Right, so factoring, solving polynomial equations. I mean, the factor and solve part of it, it's the same as with quadratics. Why do we factor? Right, so that we can have a factored form equals 0, and then we can use zero product property to actually solve the equation. We set each factor equal to 0. So that's all we're doing now. There will be a couple more methods that we didn't have before, but most of the factoring that we do is what we've already learned. And today's the end. There is no more factoring, no more new factoring concepts or methods that we learn after today. Right, these are the different methods. Right, the first one, greatest common factor. I mean, we've been doing greatest common factor. That's not different. What's different is that you might have one more layer of factoring to do. After you've taken out that greatest common factor, there may be something more to do. I mean, we had that before, but in the chapter on quadratics, the greatest common factor was probably a constant, right? Now the greatest common factor might actually be a variable term. And when you take it out, you're left with a quadratic, and so you keep factoring. Sum and difference of cubes formulas, those are two new formulas. And they're rather important in the SOL thing. Whether they're really that important in life, I don't know, but they're heavily tested. They're in the SOLs and they're heavily tested. Grouping is a method that we've actually already done. When we did the trinomials that had a not equal to 1, and you would split up the middle term, and at that point you had 4 terms, and you group the first two and you group the last term, that's what that is. I mean, if you get a polynomial with 4 terms, at this point, it probably means that if you group the first two and the last two, it'll factor. And then the last one is called a quadratic form, which means it's not a quadratic, but it can be factored like a quadratic. And then once we've gone over the different kinds of factoring, then, of course, we can solve an equation that requires that kind of factoring. Try this. So these are going to be, this is an example of the greatest common factor plus, right? Because in each one of these, there is a greatest common factor. But once you factor it out, there's more to do. Like this first one, the greatest common factor between them all is x. And when you factor an x from all those, what do you get inside? That's a simple quadratic. That's a one-step, right? What are the factors of negative 15 that add up to 2? Plus 5 minus 3. So when you're given a polynomial, something that is a degree higher than 2, most likely you're either looking at there's a greatest common factor that you can take out so that it will be quadratic, or it's going to be one of our methods that we learned today. It has to be something like that. Right, the next one, the greatest common factor between these two, right, 2 goes into both of them, and there's y is a factor here 5 times. It's a factor here 3 times. So in common, they have 3. Right? And remember properties of exponents. Y to the third times y squared. Add the 3 plus 2. You get the 5. But that's a difference of squares. Y squared minus 9. So that we did the greatest common factor plus, now we need the factor y squared minus 9. Y plus 3, y minus 3. And the last one, the greatest common factor, was 4z squared, which left a perfect square trinomial. So that's what we mean. That's what I mean, because nobody else will use these words. But by greatest common factor plus, right? First, take out the greatest common factor. Recognize what you got. So you tried this one. Try to do the same thing, right? There was a greatest common factor of all 3 of those terms was x. So when you take that out, you're left with x squared minus 7x plus 10. And that's the simple quadratic trinomial. And this is especially, I've tried to emphasize before, don't turn that into a long factoring problem. That's a one-step problem. And when you start doing factoring inside of factoring, it's, even more, you're making it even harder for yourself when you're turning that into a harder problem. Right. So what are the factors of 10 that add up to negative 7? Negative 5, negative 2. So one step now. X minus 5, x minus 2. Next. Okay, sum and difference of cubes. Quiet, please. Sum and difference of cubes. Okay, it means the sum of cubes, the difference of cubes, right? Literally. So we don't have a pattern, the sum of squares, right? But we do have a sum of cubes, and we have a difference of cubes. And if you look at the formulas here, right, here and here, you know, you have to remember them. I mean, there would be no other way to get all the problems right related to this stuff other than you know the formulas, and they're not given to you. But they're actually very similar. I mean, if you just try to remember their similarities and their minor differences, maybe they're easier to remember together than apart. Notice that these two formulas, the A's and B's are in exactly the same place, right? AB, A squared, AB, B squared. AB, A squared, AB, B squared. The only difference is the signs. And the way I remember it is, if it's the sum of cubes, then the first factor is a sum. If it's the difference of cubes, then the first factor is a difference. Right? And then what's the other difference? If that's a plus, that's a minus. If that's a minus, that's a plus. So on the SOL, when we do it, it's usually 2 or 3 of these are going to be in a multiple choice format. And it's enough if you just recognize the pattern. You don't really have to completely factor it, because you know, some of them, they won't have the right pattern of pluses and minuses, or they won't be binomial times trinomial. I mean, it has to be. If they give you 4 choices and 3 of them are binomial times binomial, then none of them are right. It has to be a binomial times a trinomial. If you just know the patterns of the formulas, you're probably going to get one or 2 out of the 3 right, just right there. You can see how in their examples they, you know, I mean, to use these things, you do have to recognize perfect cubes. I mean, you got to recognize 8 is 2 to the 3rd. 27 is 3 to the 3rd. 64 is 3 to the 3rd. 4 to the 3rd. What is 5 to the 3rd? 125. What is 6 to the 3rd? That's one we probably don't know, like right off the top of our head. 216. What is 7 to the 3rd? Come on. Go ahead. 300 and what? 14. No. 314. Okay. 7 times 7 is? You're just guessing now. I mean, are we going to go through 300 numbers? Just write down. 7 times 7 is 49. What's 7 times 49? Okay. It's not rocket surgery. 343. Right? So, I mean, if you're not sure, you're looking at a number and you suspect it might be a cube because, you know, the other one's a cube, then just do it. I mean, eventually you'll have calculators. You can do it in your calculator and check it. Is this one the sum of cubes? Yeah, because 64, we've already said, that's 4 to the 3rd. So if I write it as x to the 3rd plus 4 to the 3rd, right, then I'm using this formula. Right, so everywhere in that formula, everywhere you see an A, you're going to put an X. Everywhere you see a B, you're going to put a 4. And it'll look like this. X plus 4 times x squared minus 4x plus 4 squared, right? At that point, I'm just substituting for A and for B. But I need to simplify it as x plus 4 times x squared minus 4x plus 16. So you see the pattern, right? Since that's a sum, that's a sum. And if that's a plus, that's a minus. Everything else would be the same if it was a difference. How about this one? Does that look like it's a difference? So does it look like a difference of cubes? I mean, let's say you don't know if 250 is a perfect cube. You ought to know whether 16 is a perfect cube. Is 16 a perfect cube? No, it's not. So think of greatest common factor. Is there a greatest common factor between those terms? Well, at the very least, it's 2. Now, I might be suspicious that it's going to be 2 because 16 divided by 2 is 8, and there's your perfect cube. But, if you're thinking, well, maybe it's 4. Well, is 250 divisible by 4? I mean, remember, to check a big number, whether it's divisible by 4, all you have to do is look at the last two. Does 4 divide into 50? No, so it doesn't divide into 250 either. So we're going to factor out a 2. Okay, we're also going to factor out some x's. How many x's are in common? 2. Right, so we're taking out 2x squared. Right, what's left when I factor out a 2x squared from the first term? Well, it should be 8x to the third. And what's left when I factor 2x squared from the second term? 125. Okay, now you've got to recognize, okay, 8 and 125, they're perfect cubes. So this thing could be written as the difference of cubes. So it would look like this. 2x squared times parentheses 2x cubed minus 5 cubed. Right, and now once you see it as the difference of cubes, then use the formula right there. Right, in our problem up here, I'll just point here, you can see it, right? Up here, what is it that represents the A and what is it that represents the B? In the formula here. A equals 2x and B equals 5. So like in this formula here, everywhere you see an A, you put a 2x, 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 right? Everywhere you see a B, put a 5. It'll look like this. 2x squared times 2x minus 5, right? Because it's a difference. The first term is a difference. The first factor is a difference. And then it's 2x squared plus 2x times 5 times or plus 5 squared. All right, that's just substituting for A and B directly. And then I can simplify that. That is 2x squared times 2x minus 5 times 4x squared plus 10x plus 25. But one thing to keep in mind, when you're looking at, you're trying to compare between this and these things right here, right? Because that's a difference of cubes, right? You're going to use that formula. The B is positive 5. The minus is part of the formula. The B is positive 5. So don't use this formula and then plug in negative 5 for B. Right? The B is positive. So let's try to do number 4 first. Okay. So the A is W, the B is 3. Plug them in the formula. Remember that the 3 is positive. Okay. Try the second one. And I'll give you a clue. Definitely you're dividing out a 2. So there's the work. Yeah. Where? Here? Okay. Because 2 cubed is 8, and b to the third is b to the third. So we need to, in order to use this formula, you need to have it as a cube plus a cube, and then yeah, I mean, but again, this is properties of exponents, right? Properties of exponents say when you've got the exponent outside parentheses, then it applies to both factors inside. That was one of our properties. Okay. Now, what about the third one? Here, it's actually the number 2. What would have been the greatest common factor on that one? Y to the third, more than that? 3y to the third, right? If I take out a 3y to the third, do I have a sum or difference of cubes? Watch. 3y to the third. What's left when I factor out 3y to the third from 3y to the fifth? Y squared. What's left when I factor out the 3y to the third from negative 75y to the third? Minus 25. So this is not leading to a sum or difference of cubes. What is it? Difference of squares. So how does that factor? 3y to the third times. Emily? Come on. Y minus 5 times y plus 5. Right? That's just difference of squares. Okay, so that's all about sum and difference of cubes. Right? We started with greatest common factor, then we did sum and difference of cubes. This is the grouping. Okay, notice when you have 4 terms, it's probably going to be something that you do this to. I mean, it doesn't mean every 4-term polynomial, which has got to be at least a cubic, it doesn't mean that every one of those could be factored by grouping. But most of the time, if they give you 4 factors, it'll work out. I mean, they've made it to work. So I'm going to write it so there's more space here. X to the third minus 3x squared minus 6. That was bad. 3x squared minus 16x plus 48. Right? So in the grouping method, group the first 2 terms, group the last 2 terms. But when I introduce the parentheses for the last 2 terms, then what do I have to remember to do? The 48 becomes minus, right? Because the negative in front of parentheses is going to flip that sign to make it positive. So this is just like that step in factoring the not simple quadratic trinomial, where you had 4 terms and you grouped the first 2, you grouped the last 2, and then you did greatest common factor factoring. Now, it won't work if when you do this, you don't end up with the same thing in parentheses. But like I said, most of these, they're well designed to work. You will get the same thing in parentheses. What's the greatest common factor in the first set of parentheses? Emma? X squared. And what's left if I factor it out? X minus 3, right? And what's the greatest common factor in the second set of parentheses? Koyashi? Nope. Nope. 16. Okay, now because what's in parentheses is the same, I can factor that, x minus 3, from both of those terms, right? What's left if I factor x minus 3 from the first term? X squared. And what's left if I factor it from the second term? Minus 16. Okay, are we done? No. What kind of factoring do we do now? Lauren? Difference of squares. Okay, what will it be? Sydney? X squared minus 16, how does it factor? Difference of squares. Somebody help her out. Lauren. X minus 4 times X plus 4. Right? Again, it's a pattern you got to recognize because it comes up all the time. And there's a reason it comes up all the time because they think it's easy. They're giving you something that won't slow you down. Right? So remember, if you see 4 terms, think grouping. So try that one. Okay, I'm gonna save a step here. Watch. Group minus becomes a plus. X squared times X plus 7 minus 9 times X plus 7. X squared minus 9 times X plus 7. Okay, quiet, Peter. Okay, now, quadratic type is probably the one you'll consider the hardest. Well, maybe there's some indifference of cubes. But quadratic type is, again, it's not a quadratic, or else they just call it a quadratic. But it's of a type that you could factor like it's a quadratic. So that's why it's called quadratic type. And it comes up in just about every kind of function we do from now on. Logarithms, exponentials, trig functions, they'll do it. I mean, here would be an example of a trig function. Sine squared minus cosine squared. I mean, that actually is a quadratic. But you have to still recognize the pattern. That's a difference of squares. It's one thing squared minus another thing squared. So we have to be able to extend these patterns that we've learned with polynomials, in simpler quadratics, to any kind of function, because it still works the same, right? That would be sine plus cosine times sine minus cosine. So that's what we're going to be doing. Now we're just going to do it with higher degree polynomials. But like I say, it'll come up where you're factoring like quadratics all the time. So here's an example. I'm going to do the one on the left, and you're going to do the one on the right. So that is not 16g to the 4th minus 625 is not a quadratic, right? But we could look at it like it is a quadratic. You could even rewrite it to look like a quadratic by doing this, right? This is 4g squared in parentheses squared minus what number squared equals 625? 25. Okay, so now I've written it like it is a difference of squares, so it should factor exactly like a difference of squares, right? How would that factor? 4g plus 25, 4g squared minus 25, right? So just use the same pattern. 4g squared plus 25, 4g squared minus 25. So it was actually a quartic. Remember, that was a word for a 4th degree polynomial? But we factored it like it was a quadratic. And now we can factor one of those too. Which one? The one on the right is another difference of squares. And remember, we don't have such a thing as the sum of squares factoring. Right? That's probably going to be the seed of some kind of a true-false question on the next test, right? So how is the second one going to factor? The second factor up here. Right. What is it that's being squared here? Say again, Nate. 2g, right? This is in parentheses. 2g squared minus 5 squared. So how does that factor? 2g plus 5, 2g minus 5. So you try to do the one on the right. And it'll be, you know, it's almost the same problem. It just, instead of 625, you got a much easier number to deal with, 81. Quiet, please. What's that? Here? Well, there's going to be one plus and one minus, and the minus factors again, and the plus doesn't. Right? Okay. So I'm going to do the one on the right. But, you know, and it's similar enough to the one on the left, but you'll do the one on the left. So what's the greatest common factor on the right? 2p squared, right? So when I factor that out, 2p squared, okay, what's left inside is p to the 6th plus 5p to the 3rd plus 6. Okay, but I can rewrite that like this. 2p squared times p to the 3rd squared plus 5p to the 3rd to the 1st plus 6. Now, when it comes to the quadratic type, I mean, what you're looking at is what's in the parentheses. It's not a quadratic, but it is the type, right? It's got something squared plus something, p to the 3rd to the 1st, plus a constant. So it should factor like this, right? This will be, how would you factor it if it was p squared plus 5p plus 6? How would that factor? It's a one-stepper. What's the factors of 6 that add up to 5? 2 and 3, right? So this, if it was a quadratic, it would have factored like p plus 2 times p plus 3. Okay, but it's not a quadratic. I mean, it's still going to have the plus 2 and the plus 3, but what's the first term? It's p to the 3rd. P to the 3rd. Right? Because what we know, it needs to be that if I FOIL these two, right, I get back to this right there. P to the 3rd times p to the 3rd is p to the 6th. P to the 3rd times 3 is 3p to the 3rd. P to the 3rd times 2 is 2p to the 3rd. They add up to the 5p to the 3rd. So factor it like it's a quadratic. Just the first term's not going to be p. It's going to be something more than that. If you try to do that one, it's going to work out similarly, but not exactly the same. Okay, bye. Good luck. Don't get hurt. Okay. Okay, excitement's over. Quiet, please. Quiet, please. Right? So when you factored out the 4t squared and you're left with this, I mean, you don't always have to write a step like that right there. You don't, I wouldn't, probably. I would just recognize the pattern, right? This is fourth power, second power, constant. It could be done like a quadratic. If it was a quadratic, what are the factors of 6 that add up to negative 5? It would be minus 2, minus 3. The only question is, what's the first term? Well, what would be the first term that when you multiplied it, you got t to the fourth? T squared times t squared, t to the fourth. So t squared minus 2, t squared minus 3. Okay. Do you have a question, Nate? Yes. Yes. Because this is the to the first power. Yeah, it's always going to be that. Okay, now let's see. I think we're up to solve equations, which doesn't take long. So again, the reason why we do the factoring is so that then we can take a polynomial that's in a standard form, put it in a factored form equals 0, and then set the factors equal to 0. So I'm going to do the one on the left, and then you're going to do the one on the right. So remember, if my goal here is to do standard form equals 0, I got to move the 18x to the third to the left-hand side. So first step is going to look like this. Okay, then I can see there's a greatest common factor, which is what? 3x, right? If I factor out a 3x, I get x to the fourth minus 6x squared and plus 5. Okay, now what's in the parentheses, the trinomial, that's quadratic type. Fourth power, second power, constant. Right? So we're going to factor it like it's a quadratic. What's the factors of 5 that add up to negative 6? Negative 1, negative 5, right? So it'll look like this. 3x times x squared minus 1 times x squared minus 5. I factored it like it was a quadratic. Just in place of the x's, I put x squared. So that when I FOIL it, I get an x to the fourth. Now, am I done? Factoring. No, I mean, if you're really, the goal is to solve this by factoring as much as possible, then x squared minus 1 is difference of squares. It's x squared minus 1 squared. How does that factor? Yeah, x plus 1 times x minus 1. No. No, I didn't. I did not. I know I didn't. Okay. Here's the part you could do that we were doing before, is that you can get rid of the 3, right? You can't get rid of the x because the x, what if the x is 0? Then you're dividing by 0, right? So you can't divide out a variable that might be 0. And in fact, now that I've got this in factored form equals 0, I can tell you that one of the solutions is x equals 0, right? From that factor right there. What's the solution that comes from this factor? Negative 1. What's the solution that comes from this? 1. And then that one, if you need to solve it, right, x squared minus 5 equals 0. So x squared equals 5. So x equals plus or minus the square root of 5. Okay, and then we also had the solutions from the other factors, 0, 1, and negative 1. So how many solutions did we get? 5, right? 1, 2, 3, 4, 5, which because we started with a 5th degree polynomial, we would expect 5 answers. Now, that doesn't necessarily mean they have to all be real numbers. Now, we got 5 real number solutions there. I think the directions in the book say find all the real solutions for the homework problems. And these were. So try to do the other one. Just follow the pattern. Works out pretty much the same way. And a greatest common factor plus, quadratic type. So let me do this one quick. 2x to the fifth minus 14x to the third plus 24x. Factor out a 2x. Okay, so what's in parentheses is not a quadratic, right? But it should factor like a quadratic. So the factors of 12 that add up, quiet please. The factors of 12 that add up to -7, -3, -4. So x squared minus 4x squared minus 3. And one of those is a difference of squares, right? 2x times x plus 2 times x minus 2 times x squared minus 3 equals 0. So the answers are, right, what is it that comes from that x in front here? There it's a 0, right? And then the next factor gives us a -2, and the next factor gives us a +2, and the next factor gives us a plus or minus the square root of 3. Simple. So what are the mistakes that they've made here on the left? What did they do wrong specifically? Nathan. You can look at your notes. I mean, which one's Declan? So this is the difference of cubes, which means that should be a minus. So they used the formula wrong. What did they do wrong over here? Quiet, please. What did they do wrong on the right? Besides the fact that they actually didn't factor, they just gave us the two solutions that come from that, which is not altogether wrong, but no, not really the 3x. What did they not? The x, right? What solution should have come from the x? 0, and they didn't have a 0. So that's the mistake. Okay. So that's it. That's homework.